Right, so let me address the issue when we have a discontinuity at the cell boundaries. This is a so-called Riemann problem. And we look at it from the perspective of our wave equation example that we solved with the finite volume approach. So let me quickly mention that. So in our homework, we are solving the 1D wave equation. With this finite volume approach. Leads to this problem of approximating these cell integrals. So leads to approximating the cell, and I call these the omega E cell integrals, which look like this. So we have for each cell this integral of the mass times the acceleration, and then is equal to the stresses applied at the surface of the cell, which we can write in this way, which act in a normal direction. Usually in 1D, it's just it's a bit simpler to write down. And so in our case, we looked at a cell which goes from XA to XA plus 1, and which has like a centroid point at XP. And so this integral goes from XA to XA plus 1. Rho times the acceleration dx is equal, and now we have the stiffness term, where we have the shear moduli mu times the strain, which is the derivative of the displacement here. And we can write it in this way. So we have the mass term and the stiffness term. So where we have to evaluate now in a finite volume method, you will call it the fluxes. This mu times the derivative of s at the cell face centroids, which in 1D is just the endpoints XA and XA plus 1. So the cell corners in 1D, also the face centroids. So what we look at are these expressions, for example, at XA plus 1, which we try and approximate with this approach that we have the shear modulus at that point, times now an approximation of the derivative, where we use this central difference approximation with its neighbor point at p plus 1, divided by the distance to that one. So if you would plot that little figure, we have xa plus 1, xa, the centroid position xp with the displacement sp, and then we also look at the centroid position from the neighbor cell, which would be sp plus 1. And then we just use the central difference approximation to approximate the derivative of s at that location, xa plus 1. And so we have like our grid cell E, and the neighboring grid cell has omega E plus 1. So the question is, what's happening when we have a jump in the shear moduli from one cell to another cell? And you see we will have a jump of this flux, or which is the stress in for the 1D wave equation. So let's quickly put down that question. So what happens when we have a material discontinuity? At that cell boundary xa plus 1. So that is a jump of mu at xa plus 1 between grid cell omega E and its neighbor cell omega E plus 1. So what does that mean? We basically have now, let's say xp and xp plus 1. Here we have xa plus 1. But now we have a jump, so we have this discontinuity at the cell boundaries. So that will be sp plus 1, sp, and then we have the stress mu times, and mu comes here from the left side, times the derivative of s, and then a jump, and here we have mu from the right side times the derivative of s. Now the derivative of s itself, is continuous between the cells. The jump comes in from the material. So that the shear moduli has this jump at the cell face. So we have mu of x has this jump. It's either mu left side, when x is smaller than xa plus 1, or it has this right-hand side value when x is bigger than xa plus 1. So this leads to a jump in the stress, or if you prefer the flux, across that surface of the cell. So if you look at the stress at TA plus 1, is defined as the shear moduli at xa plus 1 times the derivative of the displacement strain at xa plus 1 t, which now becomes either the left-hand stress, oops, for, oops, let me move it a bit to the side. And x is smaller than xa plus 1, or the right-hand side stress. And x is bigger, xa plus 1. So now we have this quantity with a jump at the cell boundary. This is called a Riemann problem in the finite volume method. So in a finite volume perspective, this is a Riemann problem. We have a jump or a discontinuity of a quantity at the cell boundary. So this needs to be addressed, usually with so-called Riemann solvers. It's to be addressed by a Riemann solver. Which determines how much of that discontinuity, propagates into the cells. Into these connected cells. And so there's quite a variety of these Riemann solvers available for finite volume methods. You can try and find an exact solution to the Riemann problem, or you can find approximations to it as well. So usually when you look at finite volume methods, what you will see is the Riemann problem defined as an initial value problem for a conservation equation given discontinuity. In this domain of interest. So what you often will see is, for example, the advection problem, which is a typical problem for conservation equation. And then we have a jump of the quantity Q on the left side to the right side. So now you have this jump of a quantity and you need to address this with a Riemann solver. So if you would have the advection equation, which is a conservation equation, then you have the initial value problem. Given a jump, let's say at x equals 0, then you have Q is to the left value. If x is less than 0, or Q is right hand side value if x is bigger than 0. So this is often looked at when they explain the Riemann problem. So keep in mind that we want to have this quantity Q being conserved. So we need to find a solution how much now of the quantity goes into these cells, the left cell, right cell, such that it keeps being conserved with time. So for us, for the 1D wave equation problem, with this jump, we can also look at it from a physics perspective. So, oops. For our wave equation problem, and if let's call it a physics perspective. We want the normal component of the stress at the cell faces, the cell boundary, on an interface being continuous across the interface. So we want the normal stress at and sometimes it's called a solid-solid interface. So if you have an elastic medium, for example, with this material jump, the interface is a solid rather than a solid fluid or acoustic interface, which we would have, for example, at the free surface. But here within the Earth, we have these solid interfaces, for example. So we want the normal stress at the solid interface of a material discontinuity to be continuous. So we basically want to impose that the stress, at least the normal component in 1D is then just the stress that we compute is continuous across the interface. And the same we would also impose for the displacement. The displacement on the interface, it also has to be continuous. You cannot have a jump in the displacement at the interface. But so again, it's basically the normal component of the displacement and the stress. We want to be continuous across the interface. And so we can use that as our solution for the Riemann problem. So as for the 1D wave equation, we can take the average stress at the cell boundary. So the average TA plus 1, put it with a hat, would be the average of the stresses from the left and right hand side. So we have the stress from the left side plus the stress from the right side. And then we just take the average of these two stresses. Now we can rearrange these terms a little bit, because typically what we would just have is our stress evaluation from our reference cell, which in this case would be the left-hand side cell, UL. This would be the stress how we computed without the jump. So if we have the same material properties between the neighboring cells, then this is sufficient. We just have this as a stress, that boundary. And so we can write then like a correction to this part, which then is obviously the right side minus the left side, and take half of it. Which again can be simplified a bit, because the strain, the derivative of the displacement at that position is continuous. So we know that this is continuous. So the only jump we have are the materials. So the shear moduli, mu from the right side minus mu L. Take half of it and then have the strain. And this term here you can think of like a correction term. Which solves this Riemann problem in a finite volume perspective. So this means that if we encounter a material jump, and then this factor here of mu L minus mu L divided by 2 is non-zero, so it's bigger than 0. So then we have to add this correction term. Then we have to add a correction term, which is basically our stress difference at that boundary, which we can write here is the difference between the materials divided by 2, and then taking the strain at that position. So think of it as having our interface at xa plus 1. We have this jump at the interface. And the jump we can call this delta t. It's a jump in stress. Let's call it delta t at a plus 1. We don't really need this plus here. So the average stress would be the stress from the left-hand side, from our reference cell, plus these corrections that we would apply to it. So this is just the stress at a plus 1 coming from the left-hand side, or from our reference cell. So we have to impose this term to basically impose the continuity of stress. At the jump interface. And then what you should see is that this will lead to the proper reflection. And so if you want in a finite volume world, we can write that in terms of a Riemann solver. So there are quite a bit of different Riemann solvers in a finite volume method. And the approach here with taking this kind of average of the fluxes at the cell boundary, it will lead to something which is called the Lax-Friedrich approach for Riemann solvers. So this is related to a Lax-Friedrich approach solution. So what I found funny is that if you look at literature about the finite volume method, it's almost always applied to first order PDEs. So you would look, for example, how to put the wave equation into a first order system of equation, and then you can recast it in this sort of advection problem, and then use the typical Riemann solvers for finite volume approaches, etc., to solve this issue with jumps at the interface, for example, when we have heterogeneous materials. hardly ever saw the approach that we took here now in this class, where we actually use the second order PDE. We use the integral form of it and then discretize and approximate these integrals. But they're connected with each other, obviously. But this is kind of an alternative way of trying to solve it. And is also connected to the staggered grid finite differences that we would have. So in a finite difference world, you wouldn't have this jump of the shear moduli. So in a finite difference world, you would just define your grid, where you, let's say, compute the displacement at the staggered position and the stresses at like position xi, and this would be I plus 1/2, I minus 1/2, this would be I plus 1, etc. So you have the stresses and strains staggered with the displacement positions. And then obviously you would define here what the shear moduli would be, for example. You would a shear moduli at I plus 1/2, here at I minus 1/2, etc. But you only have one value for that grid node, for that point. So which value would you take if you would have a jump at that position? Well, probably the most simple approach is you just take the average of that. So you take the shear moduli that comes from the material from the left side, the one from the right side, you take the average of these two. And that would lead to exactly this correction that we apply here. It's going to be exactly the same then. So C is going to be related to the staggered grid approach. And probably the formulations that we have at the end, you could just come up with the exact same formulation if we look from a staggered grid approach at it. But that imposes, for example, that you have a regular gridding, etc. But so in this finite volume world that we are solving this problem here, we would have this jump, we would need to solve it in a way that where we decide how much of the stresses then of this discontinuity of these jumps would propagate, and then we would actually allow it for a nonlinear to allow for a discontinuity to propagate, or we can impose from a physics perspective, impose the continuity of the stress at the boundary, and then this will also lead it. And it would be similar to a Riemann solution to the problem. Good. The finite volume methods, you can start looking at it and you keep going deeper and deeper with the method. But it's a fun approach to solve especially nonlinear problems. So if you want to solve, for example, shock waves or nonlinear tsunami effects, then you would solve it with a finite volume approach. And for example, you could use ClawPack. That's one of the popular packages for geophysical problems to solve these conservation laws. Good, that's about it, what I wanted to add to the discussion today about this wave equation problem. And with that, we're basically all done in terms of the material and theory part of it.